Okay, so you know that if something's sitting on some sort of a slant, it's going to experience friction, right? So it's because of the same things that cause objects that are sitting on horizontals to experience friction. You know that if there's something sitting on some sort of a horizontal surface and you try to push it, say in this direction, there might be a friction force that works against it. We'll call it force due to kinetic friction. Let's assume that we get this thing moving. And applied force. What's one of the things that you need to calculate before you figure out what the friction force would be? Do you remember this? Yeah? Yeah, the normal force. And in this case, a lot of people just say, okay, so since it's on a horizontal and since the applied force is horizontal as well, then the normal force, we'll call it Fn, would have to be equal but opposite to the gravitational force. And then last week we talked about, or I guess previous to this, we talked about, well, what if there was an angled applied force? So if you push down on an object, then you have a y component to your force as well as an x component to your force. So that additional y component to the applied force plus the Fg would add up so that the normal force would have to supply sufficient force to resist both of those downwards forces. And so both of those downwards forces would contribute to the normal force, and the normal force therefore would be greater and would result in a greater kinetic friction force. And you may also have noticed in the homework that if you had a similar situation where my applied force was not down at an angle but up at an angle, then there'd be an applied force upwards, which would of course mean that the Fg being down would be slightly opposed by an upward applied force, at least the vertical component of the upward at an angle force, this y component, if you like, of the applied force. So what would happen to the normal force then? Increased, decreased, or the same? See that? Mm-hmm. Sorry? Mm-hmm. In this case here, it would be decreased. It would be decreased because you're lifting up on it a little bit. So if you lift up on it a little bit, then you're going to decrease the amount of force that the ground has to supply to keep it from falling through the earth. So the normal force would be a little bit less. And really at the end of the day, what we're saying here is, at least for this y component, for these three scenarios, we're saying that F net in the y direction for each of these would be equal to 0 newtons. And so in the y direction, for each of these, we would say that F net, if we always use the free body diagram as a way to arrive at an equation, F net in the y direction is equal to F normal plus Fg plus, if there is an applied force in the y direction, then F applied y. In the case of the first scenario, F applied y was 0. In the case of the second scenario, F applied y was downward. And in the case of the third scenario, F applied y was upwards. So we're always thinking about these components. And so this is just friction on a horizontal, which we've talked about previously and you've done homework on. Hopefully you've done your homework on it. If you haven't, and if you didn't get the homework from earlier about this specific content, please see me about it. I have extras. You can, of course, have it. Okay? But that's the old stuff. The new stuff uses all the same ideas, but we're going to change things up a little bit. Please no food in my class. I know. Anyway, you got to eat breakfast before you arrive. This is an angled surface. Okay? And I want to put something on this angled surface. We'll just use the same old box that we had before. And I want to make the angled surface be at some angle theta relative to the horizontal. I'm going to have to start adding in a bunch of forces here. The first force I think would be reasonable to add would be the force due to gravity. And as usual, I'm just going to call it Fg. And I don't want to add any numbers to this yet. I just want to start labeling this thing up. So can people see the Fg down there? Is it clear enough? I'm using a thinner marker because I want to be able to get everything in here. So I've got my force due to gravity, Fg. What's another force that could be acting on this thing? If it's just sitting there. Normal force? Now what direction would the normal force be? Because we went over this definition briefly before, but I think we need to touch on it now. Yeah? No, the normal force isn't perpendicular to the surface. I knew that's what you meant based on the way you were pointing, but yeah, perpendicular to the surface. So the normal force is off in this direction. I'm going to label it up as Fn. Now the thing is here, obviously Fg and Fn are not collinear or even antilinear with each other. There's this sort of cockeyedness here. So people say, well, how are you going to get to that normal force? Let's assume that there's no applied forces here. Let's say that the only force being applied to this object is the gravitational force. How are you going to get a normal force that somehow is the result of some reaction to the force due to gravity? Well, the normal force being perpendicular to the surface really tells us that the surface is pushing to keep this object from getting pushed into the surface. So we have to find a force due to gravity, or at least the component of the force due to gravity, that is perpendicular to the surface. And I'll show you the force due to gravity component. You see right there, if I turn this into a right angle triangle, this right angle triangle now has a component, or it has a side, such that force due to gravity is the hypotenuse. And this force due to gravity, you know what, I'm going to come up with a new name. I'm going to say it's force due to gravity that's perpendicular to the surface. And I'm going to introduce, that old upside down capitalized T, perpendicular. Force due to gravity perpendicular to the surface. And can you see that force due to gravity perpendicular to the surface would have to be equal but opposite to the normal force? Assuming that there's no applied force here, right? We're actually in a situation that's kind of similar to this one up here, only the world's just been tilted. That's all. So we've got force due to gravity perpendicular. Now, if there's a force due to gravity that's perpendicular, there's probably a force due to gravity component that's parallel to the surface as well. So I'm going to throw it on there right now, just because I can. And you can see that force due to gravity parallel is really going to be the same length as this side of the triangle. I'm just going to draw it as acting outwards from the center of the mass. Okay. Oh, I'm sorry. FG parallel. It's two big parallel lines. Looks like an 11. So it's FG with the parallel symbol beside it. If you haven't seen that symbol before, it's like an equal sign standing on end. FG parallel and FG perpendicular. Now people say, well, okay, so we've got this triangle here, we've got these forces that we've labeled up. Where are we going to come up with an angle? So I'm going to throw in a number here just for no real reason, then sometimes it helps to think through a problem if there's a number. So let's say that this guy here is 30 degrees. It looks like it might be kind of similar to 30 degrees. And I want to try and maybe draw another picture, just to blow this up to look at the geometry, okay? You don't have to draw this. I just want to write it out as an argument. So here's my scenario. You don't have to draw it. I don't want to make things too messy, but just to prove where I'm coming from here, okay? I've got my force due to gravity. I've got my force due to gravity that we called Fg perpendicular. Fg. And I want to take a look at angles. So I want to draw some parallel lines here. You see that line is parallel to the surface, the purple surface that we're looking at. That means that you see that line is also parallel to the surface. Okay. Let's go with that. Oh, this line is perpendicular to that first red line. So now I want to label up some things. I'm going to label all of the angles that are the same. That angle is 30 degrees, if it was 30 degrees. That would be 30 degrees. Okay. This guy comes down like this. Let's see now. Maybe this guy here is also parallel. Oh, this is actually not so bad. Look, isn't this also 30 degrees? And if that's 30 degrees, wouldn't this angle have to be 60 degrees? And we said before that this was 90 degrees. So what about this angle here? What is it? Got to be 30. So we've got a 60, a 90, and a 30 because there's 180 degrees in a triangle. So I want to come back to this triangle. on my previous illustration. If this theta here is 30 degrees, by the argument that we just went through, it's all with parallel lines and similar triangles and all that sort of stuff. This here would have to be 30 degrees. Okay? And if you want a more thorough proof, something that's a little bit more formal, then we could do that off to the side. I just wanted to draw a few parallel lines and some perpendicular lines and talk through it. And if you'd like to talk through those lines with me later because they didn't quite convince you, that's cool too. Or you can prove it to yourself by drawing your own parallel and perpendicular lines. In any case, that there is 30 degrees. Okay, and you can label it as such if we wanted it to be 30 degrees. Let's throw in some numbers at this point, okay? I want to make up some values. So I'm going to give some mass to these things. Let's say that this object has a mass of 10.0 kilograms. And I would like to, you know what, I should also say what the coefficient of kinetic friction is here. Mu k is equal to 0.0500. And so I want to go through a few calculations. First thing I want to do is find Fg, mass times acceleration due to gravity. Can anybody do that one in their heads? Assuming Ag is 9.81 meters per second squared. Beautiful. So Fg is 98.1 newtons. How could I figure out what Fg parallel is? Or let's do Fg perpendicular first. Can you see that Fg perpendicular is just Fg cosine of theta? Because I've got the hypotenuse, that's what Fg is in this case, and I don't have that adjacent side there. So I could see Fg perpendicular is equal to Fg times cos of theta. And in this case, theta is going to be 30 degrees. So 98.1 newtons times cos 30. Somebody with a calculator that's quick on the draw. What's 98 cos 30? Yeah? 84.95? So, 96, okay. Does anybody want to agree with that? Agree. Motion carries. 84.96 newtons. No problem. Now people are going to say, well, how are we going to come up with a directional reference frame here? Because you'll notice that this is a tilted system, right? We can't just say to the left is positive and to the right is negative or something like that. So what I would like to propose is that we tilt our reference frame. Okay? So instead of saying left and right, I would like to say negative and parallel, or positive and parallel. And you can choose to label it however you please. If you don't like that referencing system, you can come up with some other naming system. That's okay. And so if I'm going to use positive and parallel and negative and parallel, I'm also going to use positive and perpendicular and negative and perpendicular. So this guy here is going to be, would you say, negative perpendicular? Well, I'm not going to say that's an official referencing system. That's just what we're going to call it. So that's Fg perpendicular. Let's find Fg parallel. And again, if this was Fg cosine of theta, to get Fg perpendicular, Fg parallel would be Fg times sine of theta, or 98.1 newtons times sine 30. Again, somebody that's quick on the draw. Yes, sir. 49.05. Good. So that's one of those magic angles for sine. 49.05 newtons. And for direction, we could say that that's positive and parallel. All right. Now the next thing that I might want to know is, what's the friction force? What could I use here? How could I figure out the friction force? What's the first thing I need to do before I figure out the friction force? There's an assumption I need to make. Oh no, it's not frictionless. Yeah. Yeah, so I might make the assumption, since there's no angled applied force or extra angled applied forces, I might say that Fn is equal to negative Fg perpendicular, which would mean that Fn is equal, at least in magnitude, to 84.96 newtons. So now if I go to find my friction force, maybe I'll use a new piece of paper. I can say that Fk, coefficient, or the friction force due to kinetic friction, is equal to mu k Fn, or 0.0500. And you know that I have those extra zeros there to imply how to round this thing, times 84.96 newtons. Come on, Shireen, help a fella out. Sorry? 4.248 newtons. And as far as direction is concerned, anybody got a notion as to what direction it might be? Take a look at the free body diagram that we've hashed out there. Yeah, negative parallel, because if you can see here, the gravitational parallel force is going to tend to drag it down the hill, which means that the friction force is going to tend to, and I should put it on my FBD, it's going to tend to drag it up the hill. So I'll call it Fk, trying to keep it from going down the hill. Alright, so now if I wanted to, I could redraw my free body diagram with values. I've got a normal force, oopsie, Fn equals 84.96 newtons. I've got a gravitational force that's perpendicular, call it Fg perpendicular, also equal to 84.96 newtons. So if I wanted to talk about there being some sort of a net force in the perpendicular direction relative to the inclined plane, the net force would be 0 perpendicular to the inclined plane. I've got an Fk that we just calculated of 4.248 newtons, and we've got an Fg parallel equal to 49.05 newtons. Now, I never actually laid out a problem here. I just said I wanted to analyze this situation. So what could be an end thing to find here? What might a problem ask you to find in this situation? Seth? Yeah, you could find the acceleration. Now, if you wanted to find the acceleration of this object sitting on an incline, the first thing you need to do is find the net force on the system, right? In this case, it's the simple system of one object. So I would say F net perpendicular, well, I can see right just by initial analysis that it's going to be equal to 0 newtons. So I'm not going to delve into that too much. But F net parallel, I turn to my FBD and I make up a free body diagram equation. I say that F net parallel is equal to Fk plus Fg parallel, and I sub in my values. Fk, we said it was negative, so it's negative 4.248 newtons. Oh, and it occurs to me that although we called them positive and negative, I maybe didn't point out, we're also saying that's the negative direction, that's the positive direction by saying that it's positive parallel and negative parallel. I don't know if I really said that clearly enough. Plus 49.05 newtons. Should be somewhere around 45, but a little less, I suppose. .802. Thank you, Shireen. Oh, I almost dropped to 0. 44.802 newtons. And we started off with, and I didn't want to round until the very end, I guess we're not at the very, very end if we're looking for the acceleration. So 44.802 newtons. I'll just rewrite it for no particular reason. The acceleration for this system is equal to F net over the mass, or 44.802 newtons, and I'm thankful again that this mass happens to be a nice round value. We said it was 10.0 kilograms in the first place, so 4.4802 meters per second squared. And the positive value here implies that it's going to slide down the incline, or if this was like some sort of playground slide, it would be going down the slide. And rounding to significant figures, we started off with 3 sig figs, so we're going to sit with positive 4.48 meters per second squared as our final answer. Okay, so we could definitely dress this up in some sort of a story, and so I think we probably should.